Have so much fun. Thank God. I'm glad somebody does. We're just too tired.
Do you see Panos sit on? There you go, right?
He has no. He has a
I don't see anyone who looks like Maria.
I bet anything.
Hello. Oh, sorry. Bonjour. So, in keeping up with the laws here in Canada, we're going to say everything in English and in French. What did you say? Just say whatever, it doesn't matter.
Bon, bienvenue à tous. C'est la session de la réa de routage. Raise your hand if you don't understand me. Okay, we have consensus to switch in English. So welcome to all of you. That's the Rtgarea open meeting. Alvaro did the slides. So what's that? Okay. So that's the note well. If you haven't read it, please do read it before speaking in that room. And I'll pass to you, Alvaro.
Sure. Okay, you know the note well. We also have a list of other resources in the routing area. Next slide. Please, 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 please review documents. Your documents, other people's documents, anything you want to review, please review it. And also, please give us any feedback on how you think we're doing as ADs. Good to me, bad to them, of course. And I say that because you're going to give bad review about me, so you have to talk to them about me. And tell me all the good things that they're doing, because I know they're doing a good job. About how we're doing, how the area is doing, other things that you think we need to do in the area, or how do we restructure different things. You'll notice that our agenda is slightly different from what we've always had in the routing area meeting. This one is a very special meeting because we have several presentations. We don't have, for the first time in probably many, many, many years, a review of all the working groups. We do have, however, thank you. There was a working group chair who was clapping there. We do have, for the enjoyment of everyone, the wiki, so that you can still go look at the wiki. It will probably be finished by the end of the week with updates on the different working groups. So instead of everyone getting up and reading what the wiki says, we figured that we would use the time better and actually have discussions about other things in the routing area meeting. So that's what the agenda reflects here. We have 4 different presentations today that we want to share and discuss with you guys. Ross Callan is here. He came out of retirement just to be here with all of you. Yeah, that deserves a hand because not anyone comes out of retirement just to be with you guys. Then Deborah's going to talk about authors' do's and don'ts for a few minutes, and then we're going to have the 2 ANRP Advanced or Applied Networking Research Prize winners do the presentation here. We believe that there is some relationship with routing in both of them. One is a lot more obvious than the other one. The first one, which talked about routing attacks on cyber currencies. And then we're going to have Panos talk about scalable and robust identity in vehicular networks or vehicular communications. We have a special circumstance here. Panos and Maria are probably running a little bit late, so they should be here by the time we get to their presentations. Anyone want to change the agenda? Just so you know, the only change we'll be accepting is to put back the working group reviews in the agenda and read from the wiki. No? No one? Are you sure? Okay, good. So the area status, nothing or not a lot has changed. We managed to recharter one working group. One of Martin's working group, we rechartered Babel with a minor change a couple of weeks ago. And we did close one working group, LTTP extensions. This is what this looks really weird. This is what the working group distribution looks like. Apparently, I'm the only one doing any work. So let me know how good I'm doing or how bad I suck at the other working groups that are not listed here. I don't know what happened to the slide.
Do you have animation?
No, I don't have animation on that.
You should have, maybe.
Well, okay. So that's it. Yes, so this is what the Rtgarea is going to look like next time. Okay, so unless anyone has any things you want to bring up right now about the agenda, we're going to get Russ to come up here and talk about history lessons.
Do I use this mic?
Yes. This one is Russ's. And I think
So-
there.
I am tall, so I will try to, I don't know if I can make this taller or not. I can, aha. So whoever's up here next will have to deal with the fact that I set this for a tall person. I sort of had a hobby back when I used to work for a living of keeping track of ways that whole networks can go down at once. It's obviously involving multi-party interactions that are sort of unfortunate. It was a great fun hobby. And after I retired, I intended to write that down and eventually realized I wasn't ever going to get around to it. And then noticed that you guys were having an IETF not that far from where I live. And so I thought, oh, well, I'll volunteer to give a talk. And they said, oh, yeah, we'd like you to give the talk. So then it's like, oh, dear, and I'm going to I'm going to need to make slides. So I did. And John Scudder helped me with some of the slides. He's going to get up and talk about the BGP stuff. And because that's more his expertise than mine. Now, let's see if I can figure out how to make this thing work. Probably that button. What do I point it at?
Here. I think the other button.
The other button. The other button.
Okay.
The other button. Aha! No, that didn't work. Okay. Okay. So there have been some major issues with entire networks going down, some interesting things. Way back in the 1970s and 1980s and maybe even the 1990s, we did not always know exactly what we were doing. Some of this stuff was very new to us. Now that was the right slide, you can go back to it. And so some sort of interesting things happened. Since then, every now and then, you know, back when I used to go to IETF meetings, my last IETF meeting was 2 years ago in Berlin, and then I retired 2 weeks after that. So back when I went to IETF meetings, every now and then we would see somebody bringing in an idea that looked like some of the things we did wrong in the past, and old people with gray beards would say, no, don't do that. I'm a little concerned that some of us old people with gray beards are getting old, and we're not going to be around forever, and some of us aren't around anymore at all. So, except for this one talk. So I figured it would be a good idea to write this down. I never managed to write it as an RFC, so I figured I'd at least do a slide. I've tried in these slides to be completely vendor neutral. Generally, you know, the best stuff that was out there got deployed. So the stuff that did not fail this way did not fail because it was even worse, not because it was better. And, you know, we've all done this. If I had named vendors, there'd be something like 6 or 7 of them that would be named in this talk alone, and that's not counting, you know, other failures. So I wanted to be neutral, so I have not considered any issues with proprietary protocols, partly because I couldn't do that and be neutral, and also because I had enough to keep myself, the talk busy just with standards stuff. Next slide. So we're just going to jump into one particular thing, and then we'll jump into another thing and so on. Back in the 1970s, the ARPANET used a distance vector routing protocol, and then in the late 1970s, they came up with something called the new ARPANET routing protocol, which was a link state routing protocol. It used a 3-bit sequence number space because back in the 1970s, networks were pretty slow, right? I think there might have been 56K links, if that, tying the ARPANET together. With a 3-bit sequence number space, you were going to run off the end of it eventually, so it was a circular space. So when you got to the end, you went back to the beginning. And since it's a circular space, whether A is greater than B or B is greater than A, depends on which way around the circle is shorter. A single ARPANET switch, I'm sure that more than one crashed, but one in particular example that was interesting was one of them crashed sometime in the early 1980s, and when it came back up, it thought, oh well, these messages in my queue, somebody's going to want to see them, so let's forward them on. So it did forward them on, and one of the messages in its queue happened to be a routing update, which was exactly halfway around the circular sequence space from the current update, and this occurred while an update was in progress. So the 3 sequence numbers A, B, C, right? A came out bigger than B, and B was bigger than C, but C was bigger than A, going around the circular space, which meant that update A replaced update B, and then update B replaced update C, and then update C replaced update A. So, next slide. 3 routing updates chased each other around the ARPANET as fast as switches could send them to each other for hours. Fortunately, back in those days, the telephone system was not all running over the internet. And so you could call people on the phone from, you know, Cambridge, Massachusetts to someplace out in Southern California and say, please walk up to your ARPANET switch and turn it off. And so somebody had to actually physically walk up to all except 2 of the packet switches in the ARPANET and turn it off. When they were all turned off except 2, now there was only 2 updates that something thought was the most recent. And so of the 2, one of them took precedent. And so very soon there was only 1 update that that both of the switches that were still up thought was most current. And so now everybody could go manually to all of the switches in the ARPANET and turn them all back on again. This was a little bit unpleasant back in the 1980s, but it wasn't that catastrophic because, you know, the ARPANET failure wasn't catastrophic. Today, if you had hundreds or even thousands of routers in a network, this could be quite unpleasant. Next slide. We'll get a different problem. Back in the early This was sometime around 92 or 93, I think. There was a network that was stable and working well. It had a fairly modest number of routers that were basically as big as you could buy back then in the core, and it had a whole bunch of edge routers, as stubs. And it was working well, and the customer was quite happy, but the customer thought, well, I care about reliability, so let's multi-home the stubs. Next slide. So they did that, and immediately the network completely collapsed. So what happened? What happened was on the next slide. Some router, right, like that core router in the middle had a link state advertisement to send out, so it sent it to all its neighbors, including all of the stubs. All of the neighbors thought all my other neighbors are going to want to see this update, so they all forwarded on too. So they all arrived at once at another core router. It turned out, I remember at the time, people were complaining that Dijkstra was so slow. No, Dijkstra wasn't really the problem. People just thought it was. Once they actually started looking hard at the code and instrumenting it, they discovered the problem was simply getting the same link state advertisement 20, 30, 40 times all at once was too much for their little processors at the time, and it caused them to crash in various ways. Up until seeing this happen in the network, nobody predicted that this was going to be a problem, but then we saw it be a problem and networks failed and we fixed it. A similar problem can occur with IP over ATM, where you have, I got lazy because I was writing this slide, like one of the last ones I did before sending the slides in, and I didn't draw all the ATM switches in the middle. But if you have a bunch of routers all attached to an ATM cloud and you have a bunch of ATM switches in the middle or frame relay switches in the middle, you have full mesh of links between the routers. The same sort of things can happen. And so mesh groups got added to deal with that. Next slide. There's another problem that I noticed, and this I was actually pulled down into the lab in 1992, and somebody said, sit there and look at this. Network would stay stable for quite a while, and it just worked great. And then just randomly by coincidence, several things would happen at pretty much the same time. Now, in those days, back before my hair turned gray, processors were a lot slower than they are now, and the processors were also used to forward packets in addition to doing the routing protocol stuff. So if you got several changes that just happened to occur at the same time, the processors could fall behind. So even if one router was sending out its hellos on time, the next router over might not notice for a while simply because it was too busy doing other stuff. And so it might have the timer go off saying, I haven't gotten a hello in the last 10 seconds, before it noticed that it has hello sitting in its queue. And so what happens when that happens? Well, it decides I haven't got hellos for a while, I'm going to drop the adjacency. What do I do when I drop the adjacency? I then send out another update. So at the time when the network was too busy, what am I going to do? Send more traffic to make it more busy. A couple of routers do this, it's going to cause more of the same, more congestion. Other processors get busy, they drop hellos. So what I was sort of looking at in the lab in 1992 was an entire network all disconnecting at once. Now, another fun thing happened. These link state advertisements were going to be refreshed periodically with a fixed timer. So since the whole network collapses at once, they all come back up at once. It all comes back up at once. 20 minutes later, they all decide at the same time they have to refresh their LSAs. So they send them all out again, all at the same time, which means it happens again. So since I was encouraged to sit there for like an hour and watch this happen, every 20 minutes it would happen again. The whole network just goes down, the whole network comes back up, works fine for 20 minutes, then the whole thing goes down, then the whole thing comes back up. This was considered not a good thing. It was great fun though, much more fun than watching TV. Well, at least every 20 minutes it was more fun. some solution, you optimize the hello, the protocol processing, you prioritize the hellos, so you deal with them first because you never want to drop an adjacency if the adjacency is really there. You randomize the timers so that if everybody goes down and up at once, they don't all 20 minutes later get panicky at the same time. This seemed to be known to me in 92 or 93 because it was 92 I watched this all happen. In 93 I watched it all get fixed. But about a year later, there was an ATM network, pretty big one, well-known service provider that you've all heard of, had a big ATM network, and a couple, I don't know if it was 2 or 3, but a small number of links went down that happened to partition the entire ATM network. And the link stayed down long enough for all of the link state advertisements on each side of the partition to get completely refreshed while the network was partitioned. This was an ATM network that was using OSPF as its routing protocol. So at some point, one of those partitions healed, right? Or got, somebody went out there and reconnected the wire, and then the link came back up again. And so the switch on each side of that now reconnected link, they run, the database sync, and they each decide, okay, the guy on the other end is going to want to know about the entire database that I have. So both switches at each end of the link that came back up send its entire database to the other side. What happened? Well, every single CPU in the entire network got congested, dropped to lows. Every link in the entire network went down, and then they came back up again. To the credit of whoever wrote the software, they did randomize their timers. So it did not repeat every 20 minutes for the rest of all time. It only happened once, but it was still not much fun for a very big service provider somewhere. This was supposed to be a build, but apparently builds aren't working, which is probably going to be more of an issue for John than me, because I only have one build and it's not very exciting. Denial of service attacks, I guess we're all familiar with that. Some attacker manages to get software onto many, many hosts throughout the network, and they all send traffic to the same place, overwhelming a victim, congesting links. Next slide. There was a fun example of this that happened in 2003, if we get to the next slide. Oh, I guess try again. You might have to do it one more time, because I think since I had to build with 3 things, it showed you the same picture 3 times. It's not exactly what you would have wanted, but it's good enough for government work. Okay, so in January 2003, there was the slammer worm, right? It was a worm that was created that just propagated itself very rapidly. On average, it doubled every 8 seconds. So from until you notice it's there until it's causing a horrible problem is not very long. It decided what IP address to attack by just picking an address at random and trying to attack it. And if it succeeded, it succeeded. And if not, it would pick a different address at random and try to attack it. Of all of the addresses that it picked at random, some of them were the address of a router. So not only, now the routers, I'm not aware of any routers that actually got infected by the slammer worm because they had fairly special software, but they certainly got a lot of traffic sent to them. So what happened in 2003? Well, the routers dropped their hellos in some cases, and drop their adjacencies, and the networks disconnect. So apparently not everything that was learned back in the 1990s was actually completely, totally learned. However, I don't know whether this was caused by link congestion or by CPU congestion. Slammer really hit the internet very, very hard, and so almost everything got overwhelmed at the time. The other fun thing is there were some routers that were getting so much traffic that they wouldn't respond to the management plane. So you could go to the console at the router and type in commands and nothing would happen. So I know of cases where people actually had to physically disconnect all of the interfaces on the router, type in the command to filter and discard all of the packets that are causing the attack, and then reattach the physical interfaces to the router. Again, as time goes on, actually physically going to every router is not really a lot of fun. Nowadays, as you drive down the highway, you see lots of little black boxes up on the electrical telephone lines, and some of those are routers. I don't really think they have consoles attached. At any rate, this is a fun problem. Next. So same pretty much solution, but it had to be done with a little more care. Next. Oh yeah, this is a fun one. I do know who wrote some of the software involved here, and he's quite proud of it. ISIS and OSPF were designed in the mid-1980s. Back then, again, the CPUs are slower than they are now. And again, some of the CPUs are still, in fact, I think on the most part, we're still forwarding packets in the same CPU. Because of this, I don't know what funny character showed up there on the slide, but the original spec tried to minimize the strain on the CPU and optimize the speed of flooding, given that the CPUs were not super fast back then. So one of the things that the ISIS spec specifies is, first you check the outer wrapper. So you check the checksum, yep, that passes, that's good. You check the sequence number and the LSP number. Is this a new update? Yes, it is. Okay, it's a new update, flood it out. After you flooded it out, then you look at what's on the inside. These protocols had been implemented for a while. ISIS was deployed in multiple networks around the world. Most of the large service providers had it running. And it was solid and worked well, no problems at all, until the next slide. There happened to be a bad interface somewhere that was trashing packets that would just randomly change a few bits and then could forward the packet. Now, most of the time, the checksum would fail, right? And the packet would be thrown away. But one packet managed to get through, because if you randomly change one bit, the checksum will always catch it. But if you randomly change multiple bits, the checksum will catch it with something like 1 in 65,000 or 65,536 or some number up around there, that it might get through as okay. One packet happened to get through as okay, and the routers looked at the outer wrapper and it was fine. This is a new update, it's legitimate. So you forward it. Then you check the insides. The length field was out of range. Somebody forgot to check that in the software, so crash. But you forwarded the packet before you crashed. So when you come back up, somebody else will be forwarding the packet to you before it crashes. So like a whole network crashed and came back up and crashed and went, but the one fun thing was this actually affected more than one vendor at the same time. I'm not going to name any of the vendors involved because I said I wouldn't name vendors, but it was, most of these crashes have been single vendor crashes. This one was a fun one because it was a multi-vendor crash. Okay, there's a bunch of counting to infinity with distance vector routing protocols such as RIP. I could have done more slides on it, but I thought you guys probably mostly know the problem, and also, you know, there's a limit to how long I want to talk here, and there was a limit to how many slides I wanted to put together. So I just put together a couple of slides. Basically, right, you have a destination A, the router the one hop away says I'm one hop away from A, and the next router says I'm 2 hops away, and the next router say I'm 3 hops away. You don't say this back to the guy you're getting it from because that's the way you're 1 hop or 2 hops or 3 hops from, so you say it in other directions. However, these packets are sent out, you know, with some time delay involved, right? So exactly when any one router notices that they've gotten this, it might be, you know, a few seconds, it might be a few more seconds or a few less seconds. It can vary a little bit. So if A goes away at some point, and that first router says, I can't get there anymore, the next router says, I can't get there anymore, but that router sent out a thing saying I'm 2 hops away, and then it says something, I can't get there anymore. The next route over has, those last 2 routers have been hearing from each other that they can get there at 3 hops. So they think they have a 3-hop way to get there in addition to the 2-hop way, right? So well, really it'd be, yeah, that's right. So when A goes away, those routers on the right think that they can get there by each other by 3 hops. So when they hear they can't get there from the guy in the middle at 2 hops, they might say back to that guy, well, that's okay, I can get there, and it's 4 hops. However, there's going to be a timing issue as to when does one say that and when does the other hear it. So if we go to the next slide, this is just one possible thing that might happen is that guy at the bottom has just heard from the guy up on the upper right, I can get there at 3 hops. So he thinks, oh, well, I just heard from the guy in the middle that he can't get there anymore, so I'll tell him that I can get there in 4 hops. So then the guy in the middle has heard that, so he'll say to the guy over on the right, well, I can't get there by 2 hops anymore, but I can get there at 5 hops. So the guy on the upper right says to the guy on the bottom, I can get there at 6 hops. He says 7 hops. You count up to infinity, 1 hop at a time. RIP gets around this by the lovely approach of setting infinity to a fairly small number, so you'll actually get there. I think it's 15 is infinity, if it's right. It's either 15 or 16 is infinity. Yeah, it's 15, okay. Great fun. However, it turns out in the early NSFNet, they found a way to make this more fun. For that, we're going to get in. I don't know why the slides have gone to tiny, tiny little font now. My apologies. What I sent in was not tiny font, although I will admit that it was a more recent slide. For delay-based routing is something that's been tried a bunch of times with a bunch of fun things. There's been multiple, actually all of the bullets and sub-bullets have been lost too on this slide. Very interesting. It's only appropriate that for this particular talk, something would go wrong on the slides. So there have been interesting experiments with routing based on real-time queuing. One example was in the early NSFNet. This is before IBM got involved. It was back when it was a university professor and probably a few grad students or maybe even undergrad students. I'm not sure. There might be somebody in this room who could tell me. But there was a friendly professor who was building the routers for the very first version of the NSFNet. And they were called fuzzballs, and they worked, that's just sort of their nickname, and they had a real-time delay-based protocol which actually was measuring queuing delays in the router. So it would add its queuing delays to what it was hearing from its neighbor with the distant sector routing in the core of the NSFNet. So because this was, queuing delays can go up and down and up and down, right? If you have a particular path that's not congested at all, it'll have very small delays. It'll have very small metrics. Everybody will think that's a great way to go. So a whole bunch of traffic will decide to go that way. So that'll put the delay way up. And then everybody will decide to go a different way. And that'll put the, so you can sort of oscillate back and forth. Now, this was what was going on at the core of the first NSFNet. Outside of that, they were running RIP. So how do you go from RIP to the hello protocol in the middle? You have mapping tables where, you know, a RIP value of 2 would get mapped to a delay of this and a, you know, of X, and a value of 3 would get mapped to a slightly larger delay, and so on. Then you go across the core, and on the other side, it was mapped back into RIP. And it was done so that if, you know, if a particular RIP value of let's say 3 got mapped to a particular delay, when you got to the other side, it was guaranteed to be mapped to at least 4, right? But the problem is you had this delay-based protocol in the core that was flapping all over the place. And that was getting mapped into RIP values, RIP hop counts, which were flapping all over the place. So you take that counting to infinity behavior that I just mentioned, and you feed it with highly dynamic, jumping up and down metric values that you're feeding into RIP all around the edges. The early NSFNet was not the greatest success. Fortunately, they got replaced with something better. I do remember at one point I was at a meeting at the National Center for Atmospheric Research in Colorado, and I telnetted back to my home computer in Cambridge, Massachusetts, and typed in, you know, log in and did a couple of things, and then it froze. And I couldn't do anything. I couldn't log out. I couldn't stop the session. I couldn't do anything at all. 45 minutes later, it came back, and I was still logged into this computer on the other side of the country. Of course, the first thing I did was log out, right? Because I could have walked away and a student could have walked up and been logged into my computer. So that was great fun. There's been another, you know, I mean, there's all kinds of fun things that have happened with delay-based routing. Another version that was fun was, again, in the mid to late 1980s. This what they call the new ARPANET routing protocol decided to use delay, but heavily dampened. So the metrics were a combination of hop count and delay, with the contribution of delay being very, very small. So it was mostly hop count with a little bit of delay. So between equal cost paths, you take the less congested way. The problem is then the network started getting congested. And it was a linear combination of hop count and delay. So as the delays went up to 10 times as big, all of a sudden it turned into what was essentially a straight delay-based routing, became widely oscillating, routing started oscillating rather wildly, causing the network to not work very well. And of course, they had to go and update the software and change the way they were doing metrics. Next. Non-deterministic routing. This is about BGP. And John, I'm afraid your slides have been slightly mutilated, but you'll get to talk to them anyways. Yeah.
Slightly mutilated? Yeah, so fortunately, I guess this is fortunate, when Ross asked me to come up with some BGP examples, I couldn't think of as many that fall into the kind of halt and catch fire category as he came up with in the earlier slide set. But there's still some interesting history behind BGP. So one thing that I thought was kind of interesting is that we, as probably, I won't repeat this because it's generally true, but as a lot of you know, but some of you may not, we currently are routing the internet using a protocol that's neither deterministic nor even formally correct. But hey, it still works anyway, mostly. So one of the ones that I thought was really cool when I first had it explained to me by Tim Griffin was this thing called BGP wedgies, which is a great name. And there's an RFC about it, and if you've never heard of these things before, I recommend it as entertaining reading to keep you awake at night or give you nightmares. But basically the, sort of the outline is that you, BGP, if you hang out in the BGP community at all, you keep hearing things like it's a local matter or that's policy. And policy is local, but forwarding is global. And that leads to interesting consequences. Next slide, please. We'll see what happens now. Ooh, okay, we at least get to see the picture. We don't get to see the build, we get to see the whole build at once, I guess. So I normally discourage my authors from doing builds, but I really, do we have a laser? Like, does at least that much work? All right, so we'll try to do it this way, I guess. Basically, the setup, this is a relatively simple version of it, is that, this guy down here, the customer, has a link that they only ever want to use for backup. Their policy is they want to receive all of their traffic this way, even if it's coming the long way around, because, maybe these are all really high bandwidth links and that's really low bandwidth, they're really expensive, or, whatever, who cares? So they implement this policy using a community, BGP community, that they send on the route in this direction. And that community has the semantics, their locally defined semantics telling this provider, what, if you have a backup route available, please follow that one instead of the one I'm sending you. So when you set the topology up, it's all good. Traffic goes boom, 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 as desired. So now, let's see, we failed this link. What happens then? Routing does what we hoped it would do, and traffic goes this way, and that backup link that customer C has expensively provisioned actually does its work. The interesting thing that happens is when that link comes back up, because of the way BGP operates, well, let's see, how does this work? Yeah, you end up with traffic following that set of routes instead, because you have the property that you already have a route that is coming this way, which is suppressing advertisement of a route in the reverse direction, which means that in particular this AS never gets to hear about this route, and it therefore never stops using that route. It would have made more sense with the build. If you find yourself interested in this and that was clear as mud, I refer you to the RFC, which is really a pretty good exposition. But the interesting takeaway, actually, in a bunch of these upcoming slides is that very simple protocols with very simple behaviors can have complicated emergent behaviors when you put a few different features together. Next slide, please. Right, so we're going through the whole build now. I hope you enjoy it. I worked hard on it. I'll do a little soft chew, entertain you while this is going on.
How many?
There were a lot of slides in the build, so I worked really hard on it, guys.
We missed a lot. Okay, maybe.
I could grab my laptop and stand up with it. Okay, here we go. Yeah, these Chromebooks are awesome. So, yeah, you guys can't even read these. So the description for that kind of, weird behavior where you can flip from one stable behavior, have a transition, and then transition back into a completely different stable behavior is multi-stable. So interestingly enough, if once you throw the popular BGP multi-exit discriminator attribute into the mix, BGP is not even multi-stable, it's just not stable. Well, how the heck did that happen? Were the designers of BGP not paying attention? Well, who knows? But basically and again, there are RFCs you can go and read if you're not aware of this phenomenon, you find it interesting, but pretty much what causes the behavior is the BGP route selection process assumes you can find a total ordering over all of the routes. There's this cool attribute called multi-exit discriminator. It only gives a partial ordering because only certain routes are comparable, having to do with, only routes from a given neighbor AS can be compared between themselves. That's all fine so far, as long as you deploy the protocol as it was originally designed, which is with flat IBGP, meaning that every router in an AS talks to every other router in the AS and they all know each other's routes. It turned out that BGP did not scale or deploy well to large ASs that way, so we invented several things, including route reflectors. Route reflectors do data hiding. Data hiding works great if you have total ordering, but we don't have total ordering. So you can, as easily as you like, build a persistently oscillating topology. What's worse is, so of course we did not realize at the time that, it took probably a few years, and it's kind of like Ross was saying, where he had to sit and, was forced not to leave his chair for 20 minutes and said, oh, I had a similar experience with this thing. It's not completely clear that, even if the working group had been presented with this problem, the moment we realized, or the moment route reflection was proposed, or the moment MEDs were proposed, it's not clear that anything different would have happened, because there's a compelling business need for multi-exit discriminators. There's a compelling business need for route reflectors. They're both pretty easy, and once you know about the problem, you can kind of work around it. And nobody was willing, even after we realized it was a problem, to give up either one of these toys. So we have this situation which continues to obtain to this day. Next slide, please. Oh, and here we go. This is the closest I could come to an actual halt and catch fire. BGP has this, is a nice extensible protocol, and we have this thing called optional transitive attributes. An optional transitive attribute is data that basically it says, if you don't understand this data, just treat it as opaque and send it on to the next router, it's okay. So that's very nice in that it allows us to do, sort of introduce features that can roll out globally without having to have ubiquitous deployment. The problem is that PGP was also designed with fairly draconian error checking built into it. For all the best reasons. It's, if your peer sends you data that's insane, don't you think that your peer might be insane? If your peer is insane, don't you think you would prefer to stop routing through that peer? Well, yes, that makes good sense. Anybody who cares about protocol correctness can see that it's obviously the right thing to do, especially in a fully incremental protocol as BGP is, where you don't have a way of recovering synchronization once you lose it. An optional transitive attribute may not have been formatted by your peer. Your peer may not be the misbehaving party. The misbehaving party may be a really long way away across the internet. Their attribute may have, BGP basically is behaving like a replication tree in this case. So you send out one update, it gets replicated, fans out across the internet, hits a patch of routers that actually understand the attribute. They all look at it, they all say, this router, this attribute is insane, my peer must be insane, and next thing you know, all the peerings between AS1 over there and AS2 over there get reset, and people become very upset. And even though this is, in certain senses less dramatic than a lot of the outages Ross was talking about, it was also more dramatic because the internet was a little further evolved, and there were things like phone calls going over those links. So the good news is that we eventually did figure out how to fix this, basically by saying, oh, that wasn't the right thing to do, we shouldn't reset those sessions, let's not do that anymore. Next slide, please. So after having come up with these anecdotes, I tried to distill it down into, some kind of lessons learned, or lessons that ought to be learned, but they probably won't be because, being human beings, the way we learn from the mistakes of others is by repeating them ourselves. Simple protocols. BGP is a really simple protocol underneath all of the stuff. When you assemble them into large systems, can have interesting, complex, emergent behaviors. Extensible protocols are, one hates to say attractive nuisance, but they invite people to make small extensions, and small extensions are cool, but they have or can have surprising consequences when they interact. For example, the example about MED. I'm sure it's not the only example that exists. And when you invent your extensible protocol to begin with, it's got some kind of architectural integrity. But when you have people over there who are building one kind of infrastructure on top of your protocol, and people over there that are doing something completely different, they both do their little extension. They meet in the middle, and nobody knew that was going to happen. If you're serving several masters, something's got to give. If I am trying to have both protocol correctness and serve business reality, sometimes protocol correctness is going to be the one that fails. And the second last bullet actually is also something that was on one of Ross's slides, right? where he was talking about flooding before doing your check. Data that's sometimes opaque and sometimes not opaque is sometimes problematic. It's sometimes is kind of a bad word in protocol design, and if you are using it, you should probably think really hard. And finally, I love this. It's not even a paper. It's like a screed that somebody wrote a long time ago describing the worse is better design philosophy. And if you haven't read it, Google it. It's a fun short read. Basically, it contrasts, you know, why did Unix win? It wasn't because it was technically superior. It was because somebody said, yeah, well, we'll cover the 80%, and then like the 20% we'll figure it out later. It's, you know, we know it as the 80-20 rule, but yeah, you can build a virus very cheaply and get it out into the world, and you'll probably win, but then you'll have to live with the consequences, which is what we do.
I'm going to assume we're running a little low on time, right? Okay, 2 slides left. There are other examples. There have been operating errors. Signaling System 7 had some famous failure, which I don't know if any of us are an expert on, but it might be fun to compare that to things that we've done wrong. I've heard vague rumors of other people have noticed that whole networks can fail at once. I don't know if they tend to pick one of the methods we've already used or if anybody's come up with other additional ways. And I did not mention multicast. Dino smiles. Next slide. What do we do with this information? I attended an IETF 2 years ago, approximately this week, roughly in Berlin. 2 weeks after that, I retired, and I thought, I've got lots of time off. I'm going to write this all up and get an internet draft and send it off. Well, I like being retired too much. And so I figured out that was not going to happen, and I've been feeling guilty for 2 years in a row. Finally, I discovered you guys were visiting something not that far away from my neck of the woods. I'm originally from somewhere pretty close to here and still live close enough that, you know, one daughter is only a 2-hour drive from here. So it gave me an excuse to have lunch with her and drive up and see you guys. And then once they agreed to have me give the talk, I actually had to do the slides. Somebody once said that those who cannot remember the past are condemned to repeat it. I heard it as an old saying. I Googled it a few weeks ago, and it was alleged that it was said by somebody in particular who I never heard of. But I do think that it's true, right? I mean, if you don't learn from what we did wrong before, you're likely to do it again. And the old guys are getting old and getting gray and retiring and going off and doing other fun stuff. The internet today is a whole lot more valuable than it used to be. If we took down the whole internet next week, people would really not be happy, and it would make it on the news, except that nobody would get to see the news because, of course, their TVs would all be off, but they'd be mad about that too. So I'm hoping that somebody will decide this all needs to get written up in more detail. And, you know, they can bug me to try to come out of retirement long enough to read a write-up and comment on it, or to even mention some of the other people that I colluded with in putting these slides together. But just mostly I'm hoping this is helpful to guys, helpful to you people.
Okay, anybody have any questions? No questions. Hey, thank you, Ross and John. Okay, the next one I'll just do quick because I already did it in MPOS this morning, so many have seen it, and it's mostly it's a list of references for folks that are doing drafts. We've seen a lot of that recently on documents, not just in the routing area, but other areas that as they go through the different reviewers, we know there's a long chain, that there's a lot of nits picked up, and you can't expect that others find, especially technical errors, let alone editorial. So make sure you double check your document. And don't expect Diana to clean up your IANA section. They only process, so make sure it's clear. Don't hesitate to ask for help, especially ask your chairs, document shepherds, ADs, just ask for help. Don't let things sit. And then the big one right now is that if you're an author and your document's going through the publication process, don't think you can just go to sleep after the working group last call. There's much more to be done. You've got to be responsive as all these other reviewers come through with comments, because often some will comment simply, well, why did you decide this? I think you could have better have done that. And only the authors really know the history, especially the early days of the document, and why those choices were made. Do's, read your document. Make sure you have double checked it, because often sections and figures have changed in where they are. Let's see if we can fix this back. Ensure one of the authors will always be available. It doesn't have to be the same one, but because you go on vacation, but make sure somebody's available to update the document. There was an educational tutorial this last time in March on what makes a good internet draft. It was by our own Adrian and Spencer. It has very good information. So I didn't put it all here because it's a lot of information. So you should look at it and look at it twice. There's a RFC style guide, which you all should be familiar with. And something else that's been coming up is make sure that you check your abbreviations, acronyms. On first use, you're supposed to have them spelled out. And you may think they're very common. Why do we have to spell it out? But that's not necessarily true. There's a list, and there's only a few actually that have an asterisk that don't require expansion. So the best is to be on the safe side, expand everything. And something that just came up in the DetNet working group, make sure you do the reverse. We all love our acronyms and abbreviations. Make sure when you come up with what you think is a new one, check this list, because you may be surprised it's already in use, and it's not a good idea to come up with your own that duplicates or triplicates something else, okay? Because, I mean, they came up with, it was unbelievable. They had one, it was CPE, and they didn't catch it, and like, we said, wait a minute, you can't use CPE as an acronym for what you think something, it was controller, platform, some entity or something like that. And so, okay, so make sure you check in this list, check it twice, and then you all should know that there's not only you reference 2119, you need to reference 8174. So this is the phrase you should be putting in your documents. And in the routing area, we've been pulled on a couple of times, because general reviewers and stuff will come up with this. They love to have something to come up with on our documents, and there's a lot of our documents going through that we don't use the newest phrase here. So make sure you use it. Make sure you put something in your security considerations section. And we all know this one, so we've been putting, nothing new, no worries. But the security directorate won't go by that. Make sure you put something then to say, well, why is there not nothing new? Just put more than 2 sentences, and it might save you a lot of trouble. And then also for management considerations, put that you put some thought into it. And then another one that has come out, not one of our documents, but another area, make sure you're using a neutral point of view. And if you go to Wikipedia, they have lots of tutorials on it and suggestions. And make sure you're focusing on technical language versus marketing. You don't have to. Your document is now a working group document. It's going all the way through the publication process. You don't have to rationalize and bash, other IETF technologies on for why your document is the most important thing on earth and you should go forward. So make sure you're doing neutral language and focusing on technical. And of course, make sure you do your ID nits. And that's it. So, okay, so most important is ask for help, just ask for help.
So as you guys know, the IETF puts together something called the ANRP every year, the Applied Networking Research Prize. And regularly, there are winners of that prize that have research that is related to routing protocols. So we have invited the two that were awarded the prize this time to come and talk here in the routing area meeting. Maria is going to come and talk. She's from ETH in Zurich. She has a presentation about hijacking Bitcoin, how to use routing to do that.
So both of these talks, they were 45 minutes, and because we didn't want them to do a lot of work, they promised to shorten it, so they will just like skip through it. And of course, if you have any questions, you can follow up with them. But the full presentations are online.
So hello everyone, my name is Maria Postolaki and I'm a PhD student at ETH. I would like to thank you for welcoming me in this meeting and inviting me to talk here. So I will present our work on routing attacks in Bitcoin. This is joint work with my advisor, Laurent van Bever, and Aviv Zohar, who is also a professor at the Hebrew University. Routing attacks quite often, okay, wait, this is not working correctly. If you could just do full screen.
That's full screen, but
Do you think it's the next one?
No.
Next.
Yeah, but like, it's not a full slide, right? So this.
Mhm. Oh, you need to see.
Okay.
You think that will be okay.
Okay, so sorry for that. Routing attacks quite often make the news. You will have probably heard about this Russian ISP that hijack large chunks of internet traffic destined to MasterCard, Visa, and other financial services. Or about this other Canadian ISP that managed to steal $83,000 by hijacking the prefixes of a mining pool. And the price just gets higher. Recently, there was another BGP hijack against my Ether wallet that also cost multiple thousands of dollars. And that's only the tip of the iceberg in routing manipulations. By analyzing 6 months of BGP advertisements, we actually found that routing attacks happen much more often in the internet than we could have imagined. In the y-axis of this graph, you can see the number of monthly prefix hijacks that we detected in each of the months that you see in the x-axis. As you can see, multiple thousands of hijacks happen every month. Of course, not all of them are malicious. In fact, most of them are misconfigurations. But in any case, they happen and they do affect internet traffic today. The purpose of our work is to shed light on the impact of routing attacks in Bitcoin. Intuitively, Bitcoin should be robust against routing attacks, right? After all, it's a highly decentralized network of nodes that are scattered around the globe. They establish random connections, and they often use multi-homing and additional relay networks to interconnect. Unlike intuition, though, Bitcoin is highly centralized from both the mining and the routing viewpoint. In this graph, you can see the cumulative percentage of mining power as a function of the number of networks hosting it. You can imagine mining power as computational power that is used and is dedicated to Bitcoin such that it works. And networks are simple ISPs. So clearly you can see that mining power is very centralized For example, only 10 ISPs host 68% of mining power. And it's not only about the mining power. In this graph, you will see the cumulative percentage of Bitcoin clients as a function of the networks hosting them. Again, you'll see that they're centralized. For example, 13 ISPs host 30% of the Bitcoin clients. And to understand how weird this is, to run a Bitcoin client, you don't need much. Like, you don't need much CPU, you don't need specialized hardware. So it's a little bit counterintuitive. Finally, if we look at the cumulative percentage of connections as a function of the transit network intercepting it, we again see that traffic is very centralized. For example, in this case, we see that 3 ISPs intercept 63% of the Bitcoin traffic. Because of this centralization, there are actually 2 attacks that are in fact practical and effective today. The partition attack, in which the attacker tries to split the network into half, and the delay attack, in which the attacker delays the block propagation. The partition attack is very visible, as the attacker needs to hijack traffic first. However, it is very effective, even against the Bitcoin network as a whole. The delay attack is completely invisible, as the attacker will only act when traffic she naturally intercepts. However, it's only effective against targeted nodes. So that's the outline of my talk. I'll first give you some background information, and then I'll talk about each of the 2 attacks in detail. I'll finish the talk with countermeasures, including some of our follow-up work. So let's jump to the background. Bitcoin is a distributed network of nodes that establish random connections. Each of the Bitcoin clients keeps a ledger of all transactions ever done in Bitcoin. This we call the blockchain. And the blockchain is just a chain of blocks that contain transactions. This chain is extended by miners. And miners use a lot of computational power for this, so they're compensated for their effort with block rewards, Bitcoins, basically. Mining is a very risky process. You can mine for years and years and still not get anything out of it. So miners tend to collaborate, forming mining pools. And mining pools need actual Bitcoin clients to interconnect to the actual Bitcoin network. These special clients we call gateways. And oftentimes, mining pools have multiple of them that can be also hosted in different networks. If they're hosted in different networks, then we say that the mining pools are multi-home. For example, this gray pool has 2 gateways, node E and node C. And it is multi-home because these nodes are hosted in different networks. Bitcoin traffic travels around the internet, and the internet, as we know, is composed of all the ASs, and BGP is responsible for computing the forwarding path across them. The interesting part here is that all the Bitcoin traffic is unencrypted, and it doesn't have any integrity guarantee. That means that any AS in the forwarding path can actually eavesdrop, drop, delay, or even modify the messages. Note that even if Bitcoin traffic was encrypted, an attacker in the AS path would still be able to drop this traffic. I'll now talk to you about the first out of the 2 attacks that we consider in our work. So in the partition attack, the goal of the attacker is to split the network into 2 components such that no information can be exchanged between them. If I had to explain you why this is worrying for Bitcoin with 1 sentence, I would say that Bitcoin is a consensus protocol, and preventing the Bitcoin clients from talking to each other makes them not be able to get to consensus. But in a more precise way, a partition attack is an effective denial of service attack, as transactions cannot be propagated from one component to the other. It can cause revenue loss, as all blocks that are mined within one of the 2 components, the one with the least mining power, will be eventually discarded. And by discarding, I mean that the miners that they have wasted their computational power to find these blocks, they will not get any revenue back. Finally, a partition attack basically allows double spending. So I can use my same Bitcoins to buy goods in both of the two components. So now that I hope I have persuaded you that this is bad, I will tell you how this works. So let us say we have this AES topology, this Bitcoin network, and the AES in the middle wants to partition the network as denoted by the red line. So intuitively, what the attacker would do is that she would attract all traffic destined to nodes in the right, and she would drop the connections crossing the partition. To understand a little bit better how this is done, we'll focus on node F, which is the green node at the right end of this slide. So I do get that, like, now I want to explain how this will happen, but I understand that this might be boring for most of you, so I'll try to do it as quickly as possible. So node F has this IP, and AES6 is responsible for advertising the prefix, for creating a BGP prefix that covers the IP. So this advertisement will be propagated AES by AES until all of them knows how to reach AES6. So, for example, AES1 will reach AES6 via AES7. Now, the problem is that BGP doesn't check the validity of advertisement, as like folks know. As such, any AES in the internet can actually advertise any prefix. Now, let's assume that the attacker actually advertised the prefix that covers the IP of the green node, and it's in fact a longer prefix than the benign advertisement. That means that, and because routers would always choose the more specific prefix, they will all choose the attacker's advertisement versus the benign one. As such, the attacker will gain access to the traffic that is going to Bitcoin node F. And that's exactly what the attacker will do to attract all traffic destined to nodes in the right. She will hijack the prefixes pertaining to nodes in the right. She will drop the connection crossing the partition, and boom, the partition is created. Of course, creating a partition is not as trivial as I described. In fact, there are partitions that are infeasible to be created because there are connections that the attacker is not able to cut. There are three types of such connections. Connections within an AES, connections within a mining pool, and private connections between mining pools. So connections within an AES, they don't use BGP, so the attacker cannot hijack those. For the other two types, the reason why the attacker cannot do it is that she might not know the exact topology of the mining pool, or she might be unaware of a private connection. So she might not know which exact prefixes to advertise, or she might not be able to distinguish the traffic that is exchanged because of this. But even in this case, the attacker can understand that the partition she is trying to create is infeasible to be created, and instead create a feasible and similar one. So to give you an intuition, if the same attacker wants to create this partition, what she will do is that she will again hijack, and we also assume that there is this pool in the AES topology. And what the attacker will do in this case is that she will hijack all nodes in the right, so she will hijack the prefixes of all nodes pertaining in the nodes in the right. She will drop the connection crossing the partition, and the partition is created, but it's not effective. And that's because there is this connection, which is actually a stealth connection, that crosses the partition. So in fact, the partition was infeasible to be created because there is no way for the attacker to know the exact topology of the pool and being able to cut this connection. But even in this case, what the attacker can do is actually monitor the connections that she already hijacked and notice that there is information leakage between the two components. For example, it might be that the block that is mined by the black nodes is advertised by nodes by the yellow node, by the orange node. And she can even understand that the stealth connection is in node E, for example, in this case, because that's the first node that will advertise a block that should not be in this component. Once she understands that, she can change slightly the partition she wants to create in a similar and feasible one. In the paper, we actually prove that if the attacker follows this algorithm, then she can always find the maximum the maximum feasible subset of nodes she initially wanted to isolate. So we evaluated our partition attack in terms of practicality and time efficiency. To evaluate our attack in terms of practicality, we have to first infer the Bitcoin topology, which we augmented with routing information. And using this, we found out that the attacker is able to split the network into half, which is the worst case scenario for Bitcoin, by hijacking 100 prefixes. And 100 prefixes is negligible compared to the hijacks that happen in the internet often. As an illustration, in this graph, you can see on the y-axis the maximum number of prefixes that were hijacked at once in each of the months that are shown in the x-axis. So you can see that hijacks of 1,000 prefixes, which is one order of magnitude more than what the attacker would actually need, happen often, happen every month. We also evaluated our attack in terms of time efficiency. And to do that, we actually had to run the attack in the wild, so we attacked our own nodes using the following setup. So we had a bunch of nodes at ETH. They were connected to the live Bitcoin network, and we were advertising their prefix by a BGP peer in Amsterdam. As such, all traffic destined to our nodes was routed by Amsterdam. Then we attacked our nodes by hijacking their prefix via Cornell. And then we measure the time that it takes for all traffic to be redirected by the attacker's network. This time that we measure is, from this time we can infer how much time it will take for the attacker to create a partition. So we summarized our results in this graph, where you can see the cumulative percentage of connections that were intercepted by the attacker as a function of the time this took. You can see that it will take to the attacker less than 100 seconds to intercept all traffic. So that might mean that it will take for an attacker less than 100 seconds to create a partition. On the other hand, it will actually take a couple of hours for the hijack to be mitigated. And that's because it's a human-driven process. For example, it took Google a couple of hours to mitigate the Pakistan hijack. And I'm sure that most of you would have some experience with something related. We also evaluated how much time it will take for the two components to regain connectivity after the hijack has been mitigated. And we found that the Bitcoin network has some natural churn that would enable it to regain connectivity in seconds. And it will be loosely connected. The two components will be loosely connected, but still it will be able to reach consensus, which is the most important thing. I will now talk about delay attacks. So the second type of attacks that we consider in our work. The purpose of delay attacks is to keep the victim uninformed of the latest mine block. The reason why these attacks are worrying depends on the actual victim that is deprived this information. An uninformed merchant is susceptible to double spending attacks. An uninformed mining pool is destined to waste its mining power on something that is destined to be discarded, while an uninformed regular node is not able to contribute to the peer-to-peer network. So let's see how this works. In this slide, you can see 3 Bitcoin clients. Nodes A and B are connected to the victim, and we have an attacker that intercepts the connections from node A to the victim. Now, a new block is mined in the Bitcoin network, and nodes A and B learn about this new block and advertise it to the victim using an inventory message. The victim will request the block from the first Bitcoin client that advertised it. So in this case, from node A, using a get data message. Now, if the attacker wants to prevent node A from getting this block, she can either drop the get data message or drop the block itself. However, both of these attacks could fail because Bitcoin runs on top of TCP, and TCP will abort the connection in this case. What the attacker can do, though, is that she can change the content of the block message of the get data message such that a different block is requested. In this case, Node A will happily deliver the old block, the victim will ignore it, and will in fact wait for 20 minutes by default until it requests it from another Bitcoin client. And 20 minutes is a huge time interval for Bitcoin, as you have to remember that blocks are mined every approximately 10 minutes. If the attacker stops there, she would have managed to keep the victim uninformed for 20 minutes, but after the 20 minutes timeout, the victim will actually consider Node A as malicious and will disconnect. If the attacker wants to avoid this because she wants to stay under the radar or because she wants to keep this connection, what she can do is the reverse operation. So she will change another get data message of a transaction this time, such that it requests the initial block. If the block is delivered within the 20 minutes timeout, the attack is completely under the radar and the victim, the connection is kept and the victim stays uninformed for roughly 20 minutes. We evaluated our attacks in terms of effectiveness and practicality. To evaluate the effectiveness of our attack, we actually had to perform it in the wild against our own nodes. So we host some Bitcoin clients at ETH, which were connected to the live Bitcoin network, and we had an attacker that were intercepting part of the victim's connection, a configurable percentage of the victim's connections. Using this setup, we found that the attacker can keep the victim uninformed for most of its uptime, and that's correct even if the attacker intercepts only a fraction of the victim's connections. To give you an intuition of our findings, if the attacker intercepts roughly 50% of the victim's connections, she can keep it uninformed for 63% of its uptime. And if you think that doesn't often happen, then let me tell you that almost 70% of the Bitcoin clients would have an ISP that would intercept more than 50% of their connections.
I just have a very quick clarification question. When the block was modified, did the timestamp in the block get modified? Or was it just like a transaction ID or block ID? A couple slides back.
Okay.
Yeah, right there, the red block.
The 20 minutes timeout, or what are you talking about?
When you said the green block went to red, that means something in the block header was changed.
Yes.
Can you say what you changed in the
Yeah,
block header?
so basically the get data has one format, which is same for transactions and for blocks. And we need to specify which block we actually are asking for, and this will specify with the hash of the block. If you change the hash of the block to something that is an older hash, you're basically asking for a different block. Yes, and you have to recalculate the checksums, but that's it.
Hi, Brian with Nexus cryptocurrency. So if you go back to there, so there is a little bit of a delay even there in your diagram, which is what I was also what we were talking about back there with Dino. But the difference there being when you re-sign with your new hash, you still need to create a valid hash according to your hashing algorithm, which would you need to modify the timestamp right there, and you do have it. It's slightly different. It's one unit of time difference. But yeah, that was kind of just a clarification there. When you're modifying the block header to create this kind of attack, which we've also just had happen to us, and we've found a solution for. So.
Okay. Okay, so I'll now talk about countermeasures. Luckily, countermeasures exist for both of our attacks. For example, we can deal with delay attacks by adopting encryption in Bitcoin, or we can at least include a MAC in each Bitcoin message such that we are sure that nobody can modify our messages, at least without the receiver noticing it. An easier to be deployed countermeasure would be to let the Bitcoin client choose their peers in a more smart way, so in more routing-aware manner, such that there is no single ISP that intercepts most of its connections. However, dealing with a partition attack is much more challenging. The easiest way to do it is to actually host all Bitcoin clients to /24 prefixes. The reason that why this would be an effective countermeasure is because if the attacker, in this case, the attacker would need to advertise a same prefix advertisement, so not a longer one, in which case the two advertisements would be conflicting. And it is said that the attacker would be able to get back 50% of the traffic that she would otherwise intercept if she was advertising a longer prefix. And the much better way to deal with this attack is to basically deploy secure routing protocols. And this way would get away, like, we can avoid hijacks altogether. However, these are nice solutions, but they're not practical. Like, yes, of course, if we host all Bitcoin clients in /24, that would be nice, but we would increase our routing tables. And it would be awesome if we had deployed secure routing protocols, but we're not there yet. And it might be that and for sure we won't be there just for Bitcoin. So our follow-up work is on building a secure channel through which Bitcoin clients can actually communicate and exchange their blocks, even if there is an attacker on the network. So even if the Bitcoin network is partitioned, we have an additional channel that would be able to transfer blocks around. And we build these relay networks, which we call Saber. And Saber is basically a relay node. And by relay node, I mean a couple of special Bitcoin clients which are connected to each other and also to all other Bitcoin clients. And to give you an illustration, it would look like this. So we have this Bitcoin topology, and Saber network would be something like this. So you would have some additional Bitcoin clients that connect to each other, and these clients connect to all other regular Bitcoin clients in a way that regular Bitcoin clients can talk to each other via the channel, and they don't actually need to always use their direct connections to each other. And let me tell you now what is special about our Saber relay network, what's special about our nodes. So first, they are located in the internet in a strategic way such that we reduce the chances that an attacker can intercept traffic among the relay nodes or between the relay nodes and the actual Bitcoin clients. And the second thing that our nodes are special about is that they have a particularly robust design. And that's because we actually use a hybrid design for them, which is also both hardware and software. And for this, we use this new programmable hardware like P4 hardware. Okay, so now I will skip some slides because I don't have that much time. And I will actually go to the end, and I will tell you what I would want people to remember after this talk, and that's that Bitcoin is vulnerable to routing attacks, both to the network and to the node level. And the potential impact is worrying because they can cause denial of service attack, they can cause double spending and loss of revenue. However, we have countermeasures, and one of the best one would be to actually deploy secure routing protocols. And an alternative might be our solution with this relay network. And with this, I want to thank you, and I'm happy to take questions.
Anybody have questions?
Khalid from Minuk. Just regarding Sabre, how you can get against DDoS attacks? You mentioned your solution.
Okay, then I'll talk about that. All right, I'll try. Okay, so basically we deploy software hardware core design. So we use the software only to validate our blocks and to update the switch as if it was a cache. In the switch, we actually keep the block, the latest mined block. And then the switch is responsible to answer to all Bitcoin clients that it is connected to. Now, there are a few things about the switch that are very important to note. First is that these new programmable switches, they're able to process terabits per second of time at line rate. So that means that they can keep up with high demand and also with denial of service attacks. And the second thing is that we can deploy defenses in the switch itself. For example, we can deploy whitelists, blacklists, and spoofing detection and detection of amplification attacks. So we can basically deal with the network attacks in the network. Sorry? I cannot hear.
Your device is in line for mitigation from up to layer 7 mitigation you did, or just some kind of DDoS attacks?
So what I mean by DDoS attack is when, so let's assume we have a partition attack. What the attacker will also try to do is to attack the relays.
Yeah.
And to do that, she will send a lot of requests, for example. And this is the switch is able to deal with that because every request doesn't have to go through the whole stack. So it might answer right away, or it might be that it can much more quickly come up with a solution, like a filter that would stop this attacker.
Hi, thanks again. It's Brian again from Nexus. I'd love to actually sit down and talk with you more in detail, but on the slide you were going over with the mining pool itself, being, yes.
Like in the, are we talking about the background or?
Yeah, the one where you had the mining pool on the left-hand side and the good and the bad actor, or no, the one with the, so basically, this is also an attack vector on cryptocurrencies that I've seen, and it's the fact that that mining pool is actually centralized as well, meaning they can specifically be creating blocks on purpose and shutting out smaller miners, which they'd be able to do in this situation, just saying, okay, well, we want to blow away all these people who are mining on the right-hand side. All we need to do is just make sure that this guy E doesn't have connection to our mining pool anymore. And suddenly everyone loses connection in this one smaller section because it is peer-to-peer. And I think a solution for that would be for everyone to kind of start thinking in the sense that we need to have a decentralized mining pool.
So, okay, two things there. I totally agree with the fact that basically a partition attack could be used as by a mining pool that wants to win over another. So it basically removes it from the network. But yes, like the main reason why this attack works is that mining power is centralized. So if we can somehow decentralize it, yes, it will be better. On the other hand, though, what I've noticed is that mining pools, because they would lose a lot of revenue if something goes bad, they are multi-home, so they're trying to be better. So there is also an opportunity there, if we assume that mining pools are benign, which I'm not this person to say that, but like what I want to say is that it might be easier to persuade mining pools to deploy a better network rather than everyone deploying a better network. So this is a trade-off, I believe.
Yeah, I'm sorry, we have to wrap up, get the next one up. Hey, Maria, thank you very much for a very interesting topic. Okay, our next talk is on, it's not quite routing, but I think it's very interesting. It's a hot topic these days. It's vehicle communication. Thomas. Yes. Yes.
Maria?
Oh, here it is, here it is.
All right, so good afternoon. Yeah, it is afternoon still. I'm still jet lagged. So yeah, I come from KTH, and this is yet another manifestation that Sweden and Switzerland are the same thing. I mean, it's new. So usually people say, "Oh, KTH, yes, Zurich is a nice city." I mean, ETH everywhere. Now, coincidentally, secure routing is a topic that is very close to my heart, and I have done a lot of work on this in the past. Nonetheless, the topic of today's talk is totally different. So what I'll try to do is that I'll quickly go through the very first part of the talk to introduce the problem, what we're trying to do, skip a great deal of slides regarding results, and just go to the gist, the message at the end of it. And then there are very short additional topics that relate to the bigger scheme of things. And we can use, let's say, a few minutes on those and yeah, just basically see what you might be interested in. So the idea is that we have this upcoming type of systems, vehicular communication systems. You put additional computation and communication capabilities on the vehicles, these yellow arcs that allow them to communicate, and with roadside infrastructure. So basically they inform the driver about anything that is happening the driver cannot see or hear. And the purpose is to enhance transportation safety and transportation efficiency. And by the same purpose, lots of service providers are interested in throwing in some infotainment, right? And the good thing is that people are also, let's say, getting free bandwidth for those systems. Now, the problem is, if you have such a system, you might be opening the door for additional types of misbehavior. So things could go wrong in unpredictable ways, especially even if you move from a driver-assisted mode to an autonomous driving mode, where you have this communication. You don't rely only on sensors on board. And here's an example where, let's say, you have an application that informs you there's an ambulance so that you yield and slow down and yield. And then one could go and buy a box that basically fakes the ambulance traffic and then finds the way open. Right? Then there could be even more serious attacks that could basically bring down the whole system, essentially jeopardize the safety of the drivers and the cars and put their lives in danger. So there's been a lot of work on how you should be dealing with the vehicular communication. One thing that basically distinguishes beyond traditional requirements of security is the need to have both security for all networking, but at the same time have privacy. Why? Because in each of those, you have people and they care to not disclose their whereabouts. Now you might say, why on earth do they care when their mobile phone does that for them? Well, if you need to basically deploy a new technology and you say that by default it harms your privacy, you might hit the wall of some sort of regulation. So we've been working on this for many years, and our, let's say, take on this as researchers, and that's what we say, for example, to the European Commission, et cetera, is that it should be deployed with privacy in place. And looking at a very simple way of doing this, well, assuming you're digitally signing messages you're sending, you're using public key cryptography. Every time you do so, 1, 2, 3, I don't know, n messages can be trivially linked as long as someone is verifying these signatures. And the certificates can be saying everything about you. Now, you can anonymize this, but even if you do so, still the signature will give you away. So what the proposal there is to basically utilize multiple short-lived credentials and public-private key pairs, and essentially change from one persona, from one pseudonym to another as you move. And then you are trivially linkable for a short period, as short or as long as the overarching enabled applications needed. For example, a collision avoidance application is trying to figure out if someone is actually coming in your lane, et cetera, but short enough to make sure that your privacy is not at stake. And Here I'm just showing you pictures of how basically these systems on the research front have developed since our first engagement in a field demonstration from 2008 all the way to 2015, for example, here. What we're looking in this paper that I presented this morning is the provision of the credentials, because it's a different breed of a public key infrastructure. Not only you have one public-private key per entity, and a certificate that is good for a few years. But in contrast, exactly because you want to protect privacy and you want to have the lifetimes of those ephemeral credentials as low as possible, you need to provision each entity, each vehicle in this case, with many of those, huge numbers. And eventually we're talking about several orders of magnitude more credentials than any public infrastructure we have seen so far. So we split the system into domains, and we say that the duties should be separated in the sense that there is one entity, this long-term certification authority, that maintains the long-term identities of anyone registered in the system, and pseudonym certification authorities, those that provide the short-term credentials. Right? And why do we do this? So that essentially we put a barrier and we make things reversible should there be, and that's a legacy requirement, should there be some sort of accident or some other investigation, you can go back and look at these anonymized and pseudonymously authenticated transmissions and figure out which vehicle they corresponded to. But otherwise you cannot. And what we actually care to do is to consider the security infrastructure being not fully trustworthy. Essentially, we care to have a system that provides all the guarantees, the security, the privacy, the performance, as I'll show in a while. But at the same time, it assumes that the PCA and the LTCA entities I showed you earlier are honest but curious. Basically, they try themselves to figure out as much as they can about the registered vehicles. And that's the focus here. And that's exactly what we do with this design, and we care to show how it would scale. And in the end, the message will be that, well, it's not such a big impediment. You can do it with reasonably modest equipment for tens of thousands of cars. Right? We still don't have any system really deployed, but we're pushing forward towards that. So that's how it looks. Well, it reminds you, for those of you who are well versed in security protocols, it could remind you of a Kerberos-like infrastructure. The difference is that the ticket granting, the service granting tickets is anonymized. So essentially the vehicle gets in touch with the LTCA, gets an anonymized ticket that it can use to talk to any of the PCAs in the system to get a bunch of short-lived credentials, one valid after the after the other, so that it can only use one at any given point in time. And if you move from a given domain, let's say this is the Montreal municipality area to, I don't know, to the Toronto municipality area, or whatever is the split of your system, then you can talk to your LTCA, get a ticket that you can present to the foreign LTCA, and then get a new set of credentials that anyone else in that domain is actually using. Why would you care? So that when you digitally sign messages about yourself, your whereabouts, and anything else the vehicles are exchanging with each other, you don't look, let's say, you're coming from outside the system, outside the domain. That would be a trivial, let's say, very small anonymity set, if you wish to put it differently. I'm skipping parts of the policy. So basically, we worked out all the protocols. We have a system. The protocol basically can kick out entities that are found to be misbehaving, so you have revocation. And we did a lot of experimentation. Of course, we had to come up with some sort of synthetic load for this public key infrastructure. We took actual mobility traces from a city and a whole country, a small country, and we looked at different policies according to which you could basically refill with credentials, these pseudonyms, And you can think of this as some sort of fuel, right? So you get more as you go, depending what you know about your trip and so on and so forth. I don't have time to go into that. And I'm skipping, oops, the part about the policy. So one thing that matters is that you basically get to utilize all the pseudonyms you get, mostly, I mean, high degree of utilization. That's a good message to not waste computation, to not generate large sets of certificates that will never be of any use to anyone. And then we look at basically how long it takes. Here we stripped away networking delays because the whole thing is in a lab, and then the demand is virtual machines that emulate the vehicles that request the credentials. Essentially, you get your credentials in the order of less than 100 milliseconds. And that's essentially the message I was talking about. It's a complex system. It will get large and it's a complex deployment. Nonetheless, the point we're trying to make there is that not only we crank up the security and protection level by allowing honest but curious PKI entities, but also to show that this can be done with a very modest hardware, let's say, requirements. And we continue working on this, improving, of course, the system, and we're looking into how we could deploy it in the cloud environment so that we can scale in and out depending on the demand. That's a different question. We're looking at how to distribute the revocation information. That's a problem that is in general, let's say, difficult in any in classic, internet proper itself. Nonetheless, it gets even more complicated in this context. So I'll say a few words, and I'll just say a couple of minutes what we're getting there, and then I'll also say how such a system with privacy and security enabled, let's say, having these credentials could be useful in a totally different context when you try to hide from the honest but curious location-based service setup. And I will also say how you can actually take ideas from this work and liberate yourself from the need to use classic public key crypto, add some more exotic crypto in there, and then redo the system for participatory sensing systems. Right? So basically, you have input from. I will say in a minute what this is. So since I did this within, let's say, 15, 16 minutes or whatever, so maybe I'll take 2-3 minutes for the other 2-3 topics, just as a teaser, if you wish. But then there's a commonality, there's a common denominator there, and then we can have any sort of discussion you want. So let's look at the CRL distribution, certificate revocation list, right? So typically what this is sets of serial numbers, if you wish, of certificates which are no longer valid. Now, here you're having many more certificates, these pseudonyms, these ephemeral certificates. And many of them will expire, granted, but then depending on for how long you're provisioning the vehicles with certificates, you might have very large numbers. It depends when the revocation happens and how many you gave to the vehicle. So you could have a large revocation list. And of course now, since we care about privacy, what we don't want, and this is the second bullet there, is that we don't want, when we revoke an entity, at the same time to make all previous activity, all previous communication linkable or traceable. Why? Because something happened, let's say a malfunction, it doesn't matter, right? Why should you give away all the previous activities of that entity just because they no longer make part of the system? And the question is now, if you have a large-scale system with very diverse connectivity, how do you get this certificate revocation list information? You can always have online access, but there we are talking about systems where safety, humans, their well-being is at stake. So we are not. You might not want to tolerate, let's say, long delays and you want to push eventually the information to the vehicles. And one other feature that is fundamentally different is that typically you interact, let's say, with a website, a server, and you check the status of their certificate. In this case, you are in a neighborhood of previously not seen vehicles which do have certificates, but this neighborhood keeps changing. So if you were to think of some sort of OCSP type of approach, you might be hitting a wall there, exactly because you need to run this over and again. So what's the deal here? A simple idea. We call this vehicle-centric CRL distribution, and essentially we say, well, get to any vehicle only the absolute minimum information about revoked credentials that it could possibly need. And introduce some sort of cheap authenticator in other credentials, in a subset of those, or broadcast this at a very low rate. In what way or for what reason, so that essentially that CRL that you need to distribute, if you chop it into pieces, essentially you use these authenticators to basically facilitate validation of those pieces. Why? Because someone could actually fake that information if there were no security in place. You could basically claim that someone is revoked while they're not, so you kick them out of the system, or someone that is revoked, you basically modify the CRL and you let them basically act potentially maliciously as part of the system. So with these two small or very seemingly simple ideas that no one has proposed before, essentially we do get a 40-fold improvement in terms of delay to distribute this CRL information, even if though we're using around 25 kilobytes per second, like a minimum, very, very low rate of information. And this is, you might say, well, there are constraints for wireless communication, but still, we're talking about megabits per second, those links. But these are loaded links, so it pays to be frugal in that sense. Or we can have this information basically distributed over kilometers of area within very reasonable delays and extremely faster than the best solution before. So, well, that's, let's say, one problem solved further in that direction. Now, why would it be useful, not the CRL distribution, but overall having such privacy-preserving and security-enabling ephemeral credentials? Well, you can think of a scenario where you're submitting queries to an LBS server, and then every time you do this, you disclose where you are, what you care about, and eventually who you are in the end, right? So there were solutions in the literature that say, well, take all these queries, aggregate them, give them to an anonymizer, and then the anonymizer will give them to the LBS server and then shift them back to you. Fine, excellent solution. Nonetheless, it basically tells that if this guy is honest but curious, this guy is fully trustworthy. Why? It's not clear. So what we proposed is to basically rely on your peers to get this information, and if and only if they cannot provide it, then you ask the LBS. So essentially, your exposure to the honest but curious entity is minimized. But then, if you rely on peers, you could be basically getting, let's say, additional problems. Why? You could have peers which are actually misbehaving for whatever reason. So, well, we say, well, use such an infrastructure, equip those peers, whatever they are, mobile phones, cars, any sort of mobile device, powerful enough, with these credentials, and now try to solve the problem of how basically useful up-to-date information could be made available. We tried initially to have peer-to-peer epidemic distribution of this information, meaning I ask a question to the server, if I have the answer, you ask me for the answer, I'll give it to you if I have it, right? But then basically the convergence and the delay is pretty low, plus it opens additional, it raises additional questions. I could be exposing myself to my peers and so on and so forth. So to change the design here, we said that there's a randomized, not in the hands of the adversary, approach that the infrastructure randomly assigns someone to be a server node, a serving node, let's say, of the peers for a short period of time. And I'm skipping here. So essentially, we reduce dramatically the exposure to the LBS server, and with the appropriate design, we reduce the exposure to peers. And this is something that wasn't measured before. Everyone is usually a bit idealistic about these peer-to-peer interactions, but well, you never know what are the motivations, so it's the model for those nodes. And we basically deal with the problem of those basically trying to pollute the distribution of information. And for the last minute or so, same direction, mobile systems, urban sensing systems. So basically, rather than deploying a sensing infrastructure, you leverage sensing capabilities on board the cars, on board cell phones, and then you basically recruit them, quote unquote, to help you. The question is, how do you do it without giving them the opportunity to manipulate your data collection process? And how do you do it without harming their privacy? And even better, how do you provide them incentives? How do you remunerate in some way, tangible way, so that you motivate them further to participate? Now, it's a big story, and we have quite a lot of work, but then here you see, again, the same idea of separation of duty, but then here we use, I'd say, anonymous authentication for one of the entities because it suits us better, if you wish. We are not subject to standardization considerations, and so on and so forth. And we address a broader set of problems. For example, you participate in a task. The infrastructure doesn't know which task you're participating with. The only one you use those short-term credentials to submit your data because this is the computationally and communication-wise most efficient way to do it. And then you have a great deal of guarantees, which I summarize here. Well, there we also did some formal analysis of this, but we don't have time. And we went even further, and we used machine learning to basically sift SIFT, I mean, meaning that basically trying to figure out which data we can trust, even if someone, being an internal adversary, is trying to manipulate the contributed data towards basically shifting the collected data, let's say, in a way that it suits him. And that's about it. So thanks very much for the extra, let's say, opportunity to talk about this work. Okay, next time I see you, I promise I'll talk about secure routing, which is much probably close to your taste. But do you have any questions?
Okay, we're short on time, so they can always find you afterwards, and we thank you very much, Panos. And I think we'll take you up on inviting you in the future. Let us know when you're
So the funny thing is that in these networks, essentially, we work on secure geographical or geocasting, so geographical forwarding information. Yes? But otherwise, protocols are relatively simplified, basically. It's broadcast, then multi-hop relaying, and so on. But yes, thank you very much for having me.
Yes, thank you, thank you. Okay, we have only a couple of minutes. If anybody has something quick to add at the mic, if any questions, anything. And of course, you can always see us, anytime you want. Okay, so see you in Bangkok. So in C-Camp, I forgot to tell you, in C-Camp, we're going to do the menu.
Well,